Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Triangulation is brought to you by Cashfly at CACHEFLY.com. This is Triangulation, episode 178, recorded December 1st, 2014. Rob Manning, Curiosity's chief engineer. Triangulation is brought to you by NatureBox. NatureBox ships great-tasting snacks right to your door. Start snacking smarter with wholesome, delicious treats like lemon tea biscuits. To get your complimentary NatureBox sampler, visit naturebox.com/twit. That's naturebox.com/twit. And by SmartThings. SmartThings lets you control and monitor your home from anywhere in the world using your smartphone. To get started, visit smartthings.com/twit, and you'll save 10% off any home security or solution kit when you use the code TWIT10 at checkout. And by FreshBooks, the #1 cloud accounting solution that helps millions of entrepreneurs and small business owners save time billing and get paid faster. Try it free at freshbooks.com/triangulation and join over 5 million users running their business hassle-free. It's time for Triangulation. This is the show where we get together with some of the most interesting, smartest people in the world, talk about what they're doing, what their inspiration is, and they in turn inspire us to greater things. And I love doing this show, and I'm really excited about this one. Our guest is the former chief engineer at the MSL, the Mars Space Landing. He has written a book called Mars Rover Curiosity, the inside story of one of the most amazing feats in mankind's exploration of space. He continues to work towards landings, maybe even manned landings on Mars. Let's welcome Rob Manning from
Leo,
NASA
thank
JPL.
you for inviting me. Thank you. This is exciting.
I am so excited. By the way, this book is available now. Smithsonian Books, you can get it on Amazon. This would be a great gift for the holidays for any, you know what? Everybody loves space exploration. But what a geek will really love this because it is, it walks you through the process step by step with chapters with names like Avoiding Splat, Where the Devil Lies, and The Right Kind of Crazy. When did the idea for Curiosity happen, Rob?
Well, it was a slow germination of an idea. Remember, in fact, in some respects, Curiosity rover predates the invention of Spirit and Opportunity rovers.
What?
Oh, yes. In fact, the sky crane architecture goes as far back as January 2000, a month after we lost Mars Polar Lander, and 3 months after we lost Mars Climate Orbiter. 2 Mars failures back to back that just threw us on our butts. We had to figure out a new ideas. We had to brainstorm ideas on how to do this stuff safely. We were flying blind with Mars Polar Lander in so many different ways. I mean, all of our landers had so far when they land on Mars, you aim for a place on Mars that you think is safe. Well, we didn't have the kinds of camera resolution to really verify that. What's more, Mars Polar Lander, which basically, well, let me tell you, as it came into Mars, it turned its radio off, and it didn't have antennas sprinkled on around its outside of its exterior to talk to us as it landed on Mars. Now you might say, well, what does it need to say? Well, nothing really. And this vehicle didn't say anything. And its idea was that once it landed and deployed its antennas, it would then talk to Earth directly and say, hey, I made it. It was a great ride. Let me tell you all about it. Well, we never heard from it again. In fact, years later, when we finally put Mars Reconnaissance Orbiter with its fantastic spy-in-the-sky camera looking down at Mars with these fabulously beautiful high-resolution color images, we still scanned that whole area, bringing terabytes of data, and we still couldn't find it on Mars. So somewhere, Mars Polar Lander is there. I know it's there. I just don't know where or what state it's in.
And we don't know what happened to it.
Right. We never did find out. Okay, so
so that's scary. And why is it hard? I mean,
well, I think the biggest thing is that there's not like much air on Mars. Okay, you would say, well, oh, that's no big deal. There's not much air on the moon either. There's zero atmosphere on the moon. And so what's your problem? And so what we do is we could land on the moon, we take our rockets and fire the engines backwards, firing backwards to slow the descent and gradually slow until you land. Now, if you try to do that at Mars, because of the high speeds that you're coming in from outer space, even though the atmosphere is very thin, you're moving wickedly fast, 13,000 miles an hour. So when you hit that atmosphere, your vehicle will melt unless you put a heat shield. Well, that's fine. We'll put a heat shield on it, and we'll use the heat shield not only to protect it, but to help slow it down by the drag, just like the space capsules landing Apollo and the Gemini and the Mercury astronauts and the Soyuz astronauts today do coming in from outer space.
Right.
And in fact, how the space shuttle did the same thing with just a slightly different shape. Okay, so that's what we'll do. We'll just land it like we do on Earth. Mars is a bit more like Earth, at least higher up. And so that's fine, except one little detail. The atmosphere on Mars stops at the equivalent of 120,000 feet up of Earth. So if you go to 125,000 feet straight up, way up there, right on what appears to be the edges of space, that's where the equivalent density is for landing. So you're still screaming at thousands of miles an hour when you get to that density altitude. So what happens is you're going through the atmosphere fine, but you still haven't slowed down.
so it's simultaneously too much and too little atmosphere.
Yeah,
too little atmosphere to slow the capsule down with friction, but too much to
do it without it. So you got it.
It's in between the Earth and the Moon. You can't.
You got it. You're an interdescent and landing expert now. That's all it takes to know. But the only trouble is now. So we have to do something else.
Right. What was the polar lander doing? Was it parachutes? Was it?
Well, Viking. No, so Polar Lander wasn't the first lander. The first lander.
Yeah.
The Viking landers in the 1970s, and they invented the idea. So they come in with a space capsule with a heat shield on it, screaming at a very shallow angle through the atmosphere, because if you come in straight, you hit the ground. So you come in, and if you go too shallow, you bounce off. You have to be just right, and then you slow down. And when you get down to about 5 to 10 kilometers above the surface of Mars, you're now down at a two times the speed of sound, which is about the same, roughly a little bit slower than the speed of 2 times the speed of sound on this planet. So about 500 miles an hour. When you're, 1,000 miles an hour. Get my units right. So 1,000 miles an hour, and at that low densities, you can open a supersonic parachute. Now on Earth, we don't open supersonic parachutes. You really don't have to, because air slows you down. On Mars, you have to slow it down with a big parachute, and then the heat shield falls off. Now you eventually comes around. Eventually, instead of coming horizontally at first, it then comes down and tilts itself over, and then the heat shield can come off, and your lander then, which is still now coming down the parachute. Now on the parachute of Mars is still big, but the air is so thin, you're coming down as fast as a skydiver does on this planet without a parachute. Okay. So this thing's screaming down at 200 miles an hour. You're still going to hit the ground and kill yourself unless you do something else. So now this Rube Goldberg contraction has to fall away from the parachute. A rocket has to light up, slowing itself down. In the case of Viking, they had throttled engines that it looked like a lunar lander at this point. You landed on 3 legs. Right. Mars Polar Lander did the same thing, except it didn't have throttled engines. It had pulse mode, machine gun-like engines, 12 of them, that went, so it's kind of like imagine 12 machine guns bolted to the bottom of your chair. Great ride. So you come straight down to the Earth, you come down to Mars, and then it lands, so hopefully safely, on the surface of Mars. And all of these vehicles so far haven't really looked out the window. They just kind of go, oh gosh, here's the ground. I can sense it with my radar. When my legs touch down, I turn my engines off, and everything's fine.
Right.
Made it. And so that's how now before Mars Polar Lander, we had this airbag system that we came up with, Mars Pathfinder, because we couldn't afford the throttled engine. So we said, well, let's
when you say afford, what does that mean? The cost of launching all that fuel, or?
Well, in the case of Mars Pathfinder, our budget was really small.
So literally couldn't afford it.
Yes. In fact, in the early 90s, the people who knew how to build small throttle engines, the engines where you can turn up and down the thrust of the engines, didn't exist. And so we did not have either pulse mode or throttle engines available in the early 90s. So we said, let's do away with that. Let's come up with a new touchdown system where we fired 3 solid rocket motors hanging between the parachute and our lander, and those rockets would bring the system to a dead stop about 15 to 20 meters above the surface of Mars. And then once the rockets came to a stop, a cutter would cut the ropes, the airbag surrounding our lander, all the way around, would then start bouncing on the surface of Mars, and eventually roll to a stop. That we would draw in the airbags with ropes and winches, literally, and then open this thing up on any orientation, like a flower, opens itself up, flat, and now little Sojourner rover could drive off.
And it worked.
And it worked. Low budget, cheap, easy, simple, but very tricky. It took us a lot of work to get those airbags to work. We used the same identical entry, descent, and landing architecture with some modifications to land Spirit and Opportunity rovers back in 2004. And so I took the same size lander. In fact, a couple of us got together after the Mars Polar Lander failure and said, why don't we modify Pathfinder, pull out Sojourner, take the electronics box inside Pathfinder lander and put wheels on it. And that's how the Spirit and Opportunity came to be in April of 2000. Now, so we had this, so we remember we have these failures that really occurred back to back. An orbiter that became a lander. Don't do that. Doesn't work. We missed. We were supposed to miss Mars, and while we're firing engines, we arrived at Mars, but it's orbiter. But the engines, and the engines worked fine, except that we misnavigated it. And you might remember this. This is where we had the infamous math error, the imperial units to metric conversion error. How about that?
You just slap your forehead when that stuff happens.
It does. And in fact, I was right amongst the whole scenario when that was happening. And I can tell you, people say, how could you make a mistake? And as Jay Leno said, well, obviously you don't have to be a rocket scientist to be a rocket scientist. Well, I can tell you, there are no rocket scientists. We're just a bunch of human beings.
Right.
So when you work with human beings, you have to realize that one of the things that human beings excel at is making mistakes.
Yeah.
So the real trick for us is to figure out how to make up for the fact that we're human, and catch the mistakes before it's too late. And so what we did not do in the case of Mars Climate Orbiter as it approached Mars was we didn't double check what the spacecraft was telling us about how it was firing its thrusters. And unfortunately, as we got closer and closer to Mars, we realized, oh my gosh, we're too close, oh my no! Bam! It hit the upper atmosphere of Mars, and we never heard from it again.
How long did it take you before you figured out that it was using the metric instead of imperial? Or vice versa, I guess.
Much less than a day.
Tears must have come to your eye when you realized.
It was horrible. It was absolutely a horrible experience, and because it was avoidable, and the thing is, I don't want to. I can really go off in deep end and tell you about how it is we find out where our spacecraft is in our space. I mean, think about it. Here you get this little tiny spacecraft, 100 millions of miles away, right? How do you know where the heck it is? I mean, where? It looks out the window. Like, what see? It's these stars.
You don't have GPS on Mars.
No GPS on Mars, no.
I think part of the problem, Rob, is that you guys are so good at what you do and have so many successes that we start to take it for granted. We think, oh, well, it can't be that hard. Look, we're doing it all the time. And so it's really important to understand that what you're doing is the impossible. You're just really good at it.
Well, I think we are relatively good at it. We still make mistakes.
Not perfect.
So one of the things, to be honest with you, if you think about Mars Polar Lander and the Mars Climate Orbiter, we had these two failures. What did it do? It forced us to be humble and rethink from square one. It was literally a month after Mars Polar Lander disappeared that my teammates and I got together and we conjured up all sorts of new ways of landing safely on Mars that we had never stopped to think. In some sense, success is a terrible way to learn something because you get arrogant.
You get cocky.
You get over. Exactly.
Yep.
You've got to remember that just because it worked doesn't mean you're always right. And being good means being humble and being willing to accept new ideas. So we tried out these various ideas, and to our shock, we found several goofy ones, including super large airbags that unfolded the vehicle actually with inflatable ramp.
So amazing.
All these different things. And so
I'd love to have been in that boardroom or wherever it is you do that. What do you sit around a table and brainstorm? How do you come?
Yes, and because when you're doing this, it's got a real cartoony feel because you don't have time to do all the detail engineering.
Right.
So in some sense, you're drawing cartoons, and some of them were just actually putting cartoons together in PowerPoint. Literally. I mean, what I consider my biggest skills is making cartoons.
Yeah.
And that's the idea, is to communicate ideas to people. From there, the real work happens. It's great to say, I helped with, a bunch of us came up with the idea of lowering down on the ropes. But that's the easy part. The hard part is then follow through and going through every little subtle detail. Here's an example. Okay, so you've lowered this vehicle. You're hanging, your rover now is hanging on a rope, and you're trying to lower it extraordinarily slowly. In fact, Mars Science Laboratory, Curiosity landing was the slowest lander on anybody, anywhere you will find. That nice thing about the descent stage being up with this rockets up there is if you're willing to spend the fuel, you can take your jolly time and not worry about digging craters.
Right.
And so you can just lower it down. Now, kind of a key detail, though, is that these engines, which were throttled, like Viking, we had to reinvent that technology. So as they came down, if the throttle changed setting, what you didn't want to do is have the thing go boing, 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 boing. And so one of the things we realized is that when we first came up with the idea, we thought we'd use really stiff rope, Kevlar, or Vectran, or Technora, this very, very strong fabric stuff. So we held on to it, and we put that in our simulations, and guess what happened? Doing, 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 and there was a reaction between the control system in our software and the rope in the vehicle below. And we realized, oh my gosh, we've got to put a rubber band in there. So we actually had to soften it by putting nylon instead. And so this thing may go bang, 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 but this thing down here doesn't feel it because there's a rubber band.
Shock absorbers.
Exactly. So these are the kinds of things where you really find out how well these ideas are going to work or not. And it really took us years. In fact, we didn't even decide that using this descent stage and sky crane architecture of lowering the rover down on a rope and lowering it to the ground until about late 2002, and so early 2003. So that was about
just before launch. Launch was August, right?
Well, no, I'm saying this is for we were doing this thinking while we were building Spirit and Opportunity.
Oh, I see. Back then.
Yeah,
you were planning for Curiosity. Got it.
So we had the same. So remember, the entry descent landing community is not that big. So we're busy building airbag bouncing landers. Meanwhile, we're thinking about how to build and design this new system that can land something larger. So the bigger question is, why? You asked the question at the beginning. Why were we thinking about Mars Science Laboratory and Curiosity rover? We felt it was necessary to be able to build a rover that is big enough to contain laboratories. Now, Spirit and Opportunity do not have laboratories in them. They do not do sample analysis on Mars. They do look out the window. They have spectrometers on the end of the robotic arm. They have what's called a rat, which is a device that grinds away at the top of a rock. But they're roving geologists. Roving geologists a great thing. And if you, I've said
And that's the space lab, science lab here, the MSL.
No, so Spirit and Opportunity were the two little.
They were just looking around. They were just tourists.
They were tourists, but no, they were more than that. They were roving geologists. Now, roving geologists don't need a lot of equipment to go with them. They just need to be able to rove. Now, we hadn't really driven all Mars. All of our landers had been stuck,
right,
other than little Sojourner rover, which is about this big and about this tall, and it was as big as a microwave oven. And it was able to drive around the area of your backyard, very small, and it did.
Is that all really?
Yeah. Sojourner really had to keep within eye distance because we could see over the horizon. We can see, over the rocks. But if this little rover disappeared behind it, we wouldn't be able to control it,
right?
Because it's on a radio communication with the lander. So the lander, Pathfinder lander, was the one talking to Earth, and the Pathfinder lander was then chatting with the rovers. How you doing over there? Here's some more information you need from Earth, from the team back there. So the rover was in fact electronically tethered by radio with the lander, and by the cameras on the lander as well that had stereo view. The poor little rover was so close to the ground that even the biggest rocks were daunting and scary things. In fact, that was the kind of mission we learned how to drive a rover on Mars. No question. Sojourner was a huge, huge intellectual leap for us. But we discovered that you needed a bigger rover to drive around. So Spirit and Opportunity were conceived in 2000 after the sky crane was invented, architecture was invented, and as a way to be able to drive on the surface. We had never really, until Spirit and Opportunity arrived on Mars, we'd never gone very far at all. We hadn't gone, in fact, even our vision, I don't know if you know, Spirit and Opportunity, our design goal was 600 meters, less than a kilometer.
Wow.
Now, of course, and it was designed for 90 Mars days because the solar panels wouldn't survive the dust accumulation of a whole Mars year that we could see that we measured on Mars Pathfinder. So, unbeknownst to us, there was nature has its own invisible Martians that come along and squeegee our solar panels. They're not invisible Martians. They're these wind events that sandblast the very superfine dust off of our solar panels. And lo and behold, our vehicles lasted and lasted and lasted. Spirit lasted 7 years. Opportunity has now been on Mars for almost 11 years, coming in January.
And still pictures coming back. This picture of Vidoviac Ridge is from just last month.
Isn't that gorgeous?
Amazing.
Yeah. I know.
Now, you say roving geologists, can they take core samples? They can't do anything. They just look around.
No, they can look around. They can smell the rock by putting this arm up against a rock, and it could grind off the weathering rind a little bit, so you can see closely at the crystalline structure, and a little bit of spectroscopy on board, mineral spectroscopy, to get a little bit of sense of the iron oxides. And a few other details, as well as the elemental composition using alpha particle X-ray spectrometer, a little device that counts the number of atoms at different sizes. And so it's very useful as a roving geologist. What scientists wanted, and we knew back in 2000 that this is what scientists ultimately wanted, was a way to do in situ scientific analysis of the minerals and chemistry of Mars. If you're going to look for ancient life on Mars, for example, you're going to have to, it's not good enough just take a picture of layers of rocks, but you also want to grab it and taste it, put it in a device that actually measures the molecular and crystalline structure of the actual samples. And that's what we needed. And those laboratories are not small. On this planet, if you're going to do, in fact, I give a little story. If you ever get a chance to go on a field trip with a geologist, say yes. They're wonderfully fun. They will take you through the desert or through the mountains, and they will tell you by looking at it what's going on. You can see the layers. You can see the ordering of events that have happened. You can tell just from the shapes and the textures what that material is made of and the colors. So roving geologists are great because they'll do science in front of you in real time. Now, you go on a field trip with a geochemist.
Different thing. My dad's a geologist. I've been on many a field trip, and you're exactly right.
Roving geochemists are very...
It's a different thing.
They go and take samples, and they say, what you looking at? I don't know. I'm taking it to my laboratory back at the university.
Dad, we'd drive by outcrops. We'd stop at every outcrop along the way, and he'd say, well, you see the stratigraphy here, you could tell. And you're exactly right. Anyway, we're going to take a break. This is so great. We're talking to Rob Manning. He's still working on Mars, and there's two more things I want to talk about. Hey, let's get to Curiosity, the amazing landing, and the science that the Mars Science Lab is doing right now, what we're learning about Mars. And then I want to talk about the next chapter, the future of Mars exploration. I'm very interested in what our plans are. Rob's book, Mars Rover Curiosity, is really great. You can get it at Amazon. Is there an audiobook version of this? I should look.
Yes, there is.
Awesome.
Yes.
So you can get it at audible.com as well. And of course, if you have a geek in your life, a college student, somebody who wants to know more about space exploration, maybe a budding rocket scientist, this is a great place to start. The actual process of doing this is fascinating. Mars Rover Curiosity. More coming up in just a bit with our guest, Rob Manning. Our show today brought to you by, Rob, I'm going to share some snacks with you. NatureBox. NatureBox.com/twit. NatureBox gives you a chance right now to get a complimentary trial box. If you've seen us talking about NatureBox, you could get some snacks for free right now. If you go to NatureBox.com/twit, you just pay $2 shipping. So drop the candy bar, drop the potato chips, get away from them. They're no good for you. And get instead some delicious, wholesome snacks at naturebox.com. Look, we've got dried cherries. By the way, these are all in resealable bags, so you can just have a little treat, seal it up again, and have more later. The blueberry nom-noms are phenomenal. These are blueberry with oat cookies. And you notice, first of all, nutritionist approved, all of these are designed with 0 artificial flavors, colors, or sweeteners, 0 grams of trans fats, and no high fructose corn syrup. You'll even find snacks with no added sugar or without gluten. You can choose vegan, gluten-free, all of that. So in the afternoon when you're hungry, don't rush to the snack machine. Don't go have a candy bar. Instead, have a whole wheat raspberry figgy bar. Now that's good eating. Garden tomato crunchies, apple pie oat clusters. They literally have hundreds of snacks. Lone Star Snack Mix. This is good. It's spicy. They've got sweet, savory, and spicy. And by the way, here's a nice thing to say. For every NatureBox you order, the company will donate a meal to help feed millions of Americans who go hungry. In fact, their goal to donate 1 million meals by the end of this year, and you can help. Delicious, wholesome snacks for you and for a meal for a person or family in need. Isn't that nice? 1 million meals. Start your trial today. Get a complimentary sample box. Naturebox.com/twit. Stay full, stay strong, start snacking smarter. Naturebox.com/twit. And we thank NatureBox for the good work they're doing and the great treats they send us each and every month. Rob Manning is here. We're talking about Mars. I'm excited. So Curiosity, what an amazing... We were talking about all that you had learned from prior failures, and of course, one can't call opportunity a failure. It was a surprising success. Still is doing science, but you wanted more. You wanted to put a science lab on Mars. You wanted to put a geophysicist on Mars.
Yes, a geophysicist, a geochemist, people who can understand not just the high-level mineralogical structure, but specifically what are the chemicals, what are the molecules. And if you're looking for signs of ancient life,
ooh,
that is what you need. You need a way to decipher the organic structure of any organics you might find stored in the rock. So the first thing you need to do is go to Mars and find a place where organics might be stored on Mars. So where do you go? Well, the thing that scientists on this planet do, they look for ancient lake beds or aqueous water-based sediments that produce very, very fine layers. So fine phyllodoe layers, so close together, called phyllosilicates. And those phyllosilicates are so good at preserving organics that maybe if you can find one of those places, you might find sources of places where organics might be stored. But to even do that, you have to make sure that these phyllosilicates are built up in an environment where organic life might be even physically possible. For example, if we go back to Opportunity's landing site back in Meridiani Plenum, which is the big flat plain where all those little blueberries were laid out. You remember that? Mm-hmm. We have found that the chemistry, the mineralogy, not the chemistry, but the mineralogy of that place could only have been formed under rather acidic conditions. There was water there. In fact, what's so cool about Spirit and Opportunity, they both, in two sides, on both, they live on either sides of the planet of Mars. One was here, one was here. They both found that water had altered the very structure, the mineralogical structure of lava rocks that had been there millions of years earlier. So it looks quite clear. It was cool thing about those two rovers is they confirmed without a doubt that water had been present on the surface of Mars, altering the rocks, the very, very structure of the atomic structure, the molecular structure, and the crystalline structure of rocks. Okay, producing gypsum and many other minerals that we know and love on this planet. Now, but again, they found that they were formed under conditions which really weren't that habitable for life. It was just too acidic. That water was not a good place. You couldn't drink that water safely. So, we find a new landing site in the bottom of Gale Crater, and this Gale Crater, at the middle of this crater is this big mountain. Now, it's unusual to find a big mountain in the middle of a crater.
Yeah.
Not at all. However, this mountain is not a mountain. It's not the kind of mountain you'd find in the middle of a lunar crater. Why is that? It wasn't because a lunar crater is created when the asteroid slams as a meteor into the surface, and it produces this bowl-shaped structure, and then a rebound produces a mountain peak in the middle.
You've seen it if you've ever seen those slow-motion pictures of a drop of water hitting the water. It's exactly the same thing, the ejecta, and then the whoop in the middle.
That's right, and Gale Crater might have had that, but that's not what this mountain is in the middle of this crater.
Well, what is it?
It is an enormously different thing. It is a layer cake of alternating kinds of sediment that it's 16,000 feet deep, right? 16,000 feet deep. That whole crater was once covered all the way across, we believe, with sediments, both waterborne and windborne sediment that covered that whole crater. That whole massive, 80 to 100 kilometer diameter crater is completely covered, 16,000 feet. Then over billions, and this happened long ago, 3.5 billion years ago, it was covered. And then over time, it got worn away and blown away due to winds carving around. And so just like the Grand Canyon, all those layers are stacked up. And you can see, Grand Canyon, the whole place is covered, and then water cuts through and makes a crack. And you can see all the layers inside. You can go back in time to the bottom. You can see all the layers laid on top. On Mount Sharp, the mountain in the middle, those same layer cakes exist. Instead of being a point this way, it's a point this way, because it was whittled out from the outside, leaving this incredibly strange layer cake of a mountain that's 16,000 feet high, way up there. We said we could see those layers from space. So when we selected Gale Crater, we said, hey, if we can land right next to this mountain, we could then explore those layers, especially the ones near the bottom, and look at places where maybe you might find clays, phyllosilicate clays, that preserve organic residue that might have existed billions of years ago. And we might be able to find out whether those clays were laid down under conditions that would have supported life as we understand it on this planet.
So water is such a prerequisite for life that's where you start.
That's right. So from space, we can see with a very special set of instruments on both Mars Express and Mars Reconnaissance Orbiter, you can see the mineralogy from the colors of the surface of Mars from space. So from there, we say, hey, those look like phyllosilicates. There's a whole bunch of different minerals that were probably laid down under conditions that were not that acidic, that were maybe more just right. Let's go find out. So we landed Curiosity there, and instead of taking...
Was that the only goal for the MSL? No. But it was a big goal.
Our goal was our number one goal, which we succeeded in answering on our very first drill attempt into these clays at an area called Yellowknife Bay, because it looks a bit like a bay, where these flagstone pavers are lying around. Looks literally like flagstone. We went and drilled right into those, and we pulled it out, put them into our laboratories, and we discovered that those clays and the conditions inside those clays were not only conducive, not only was it wet.
It was wet? You detected water?
No, it had been wet.
Had been wet.
Formed billions of years ago under wet conditions.
Yep.
It was neutral conditions. It was water that you could drink. It was water that it was the minerals that are mixed up had the right, weren't too salty. It had the right balance of oxidizing and reducing chemicals that would have provided food.
Wow.
For certain kinds of chemotrophs that could have lived on Mars, and these single-cell organisms that could have lived there. So we basically answered the question, was Mars habitable for life 3.5 billion years ago? Yes.
Yes.
Yes, it was. At least at this spot, it was habitable. And we see other places that look very much like it, other places on Mars. So we believe that 3.5 billion years ago, Mars was a place that life could have lived. Now, this is at the same time when chemotrophs were doing that same kind of jazz over on this planet.
Isn't that interesting? But
Yes.
that means the prerequisites for life were there, but not necessarily that life was there.
Bingo. So now we go, okay, this place not only could have supported life, but because all those phyllosilicates are there, if we look around, maybe we'll find a place where those organics, if they existed, are stored as a very fine layer into that layer cake of clays, phyllosilicate clays. So our mission has been, ever since that discovery, is to go out and hunt. Now we've been on our path. Now we landed away from just at the foothills, just near the foothills of this big mountain. And now we've been driving ever since we landed a little over 2.5 years ago.
Yeah,
we've been driving and trying to get there.
You're getting close.
We are basically at the base of the mountain, and now we're exploring those layers and looking how the layers change with time. And our hope is that we will see someday a little black line of like a line of shale or line of organic residue that might tell us that life was present at one time. Very exciting. Now, again, this is a bit of a hunt. Even on this planet, it turns out when you go back and look something that old, and there's very few rocks on this planet that you can actually go out and see, as you probably know, that are that old.
Right.
Because plate tectonics and weathering, they're really hard to find on this planet. Mars, on the other hand, if you find places where the wind is scoured away, like we are now, there it is. It's right there. It hasn't been subducted into the planet because there's no subduction on Mars. So we have found this ancient place, and even on our Earth, it's difficult to find organics that are that old. So it could take us a while of hunting and pecking through these layers, and with luck, cross your fingers, we will find more opportunities for layers to see where life might be stored, ancient life, the residue of ancient life.
And of course, learning that life existed on Mars tells us it's not uncommon, it's not rare, that we are not unique and probably not alone. That's the purpose of such a investigation.
I think exactly. I mean, first of all, if you think about the web of life on this planet, this life got started incredibly early in the history of our solar system on our planet. Now, is that because our planet was the kind of the Goldilocks planet?
Right.
Everything was just right? Or is it possible that this phenomena of life is something that happens, that nature enables, and if the conditions are right, and you have the right disequilibrium between warm and cold, salty, not salty, high pH, low pH, and your right conditions and there's energy to keep those disequilibrium going, you can actually keep and sustain life for billions of years, and life itself can participate in the very act of its own survival, going, and as it did, life literally altered this planet many times over its early history. So, and it didn't do it willingly. It just happened. But our question is, well, if Mars was just right, why couldn't it have happened then? Even if life couldn't have started because the conditions weren't perfectly right, why isn't there life now anyway? The reason I say that is just because, as you know, we have found rocks from Mars on this planet. There are rocks that have been found by scientists in Antarctica, in the Sahara Desert, all over this planet. We have found rocks. We have confirmed, without question, contain Martian air trapped in those rocks, and it matches the same isotopic ratios as we have on the atmosphere on Mars. So we know those rocks came here. How did they get here? Well, a meteor or an asteroid came along, slammed into Mars, threw up the Mars rocks. The Mars rocks went into orbit around the sun by themselves for millions of years before slamming into this planet thousands of years ago. And we have found at least one rock, ALH 84001, which is a famous Allen Hills meteorite that was discovered. It landed in the 80s and was announced in the 90s as possibly containing signs of organic structures, or what looked like life. Now, since that time, we've convinced ourselves, those structures, in order to prove and to say it's life, we need, as Carl Sagan said, extraordinary claims require extraordinary evidence. This was really amazing evidence, but we have also found that there are possibly inorganic methods to produce those structures. So we cannot say that those structures in that meteorite is life on Mars, life from Mars. However, we thought that might be the case in the 90s. We're saying, well, no, maybe not. But we did learn something else from this meteor. We learned that it is possible for at least theoretically possible, for life from Mars, if they had been there, to travel to Earth and land here and survive. We did the math. It works out. Even after millions of years, it's possible for life to put itself in a sporophoric state for long periods of time deep inside a rock and have it escape on this planet. Now, did that happen? I don't know. Maybe, maybe not. Well, what about the reverse? Has Earth life, which we know lives here and lives in huge quantities in our own rocks, could it possibly be that life on this planet has made a trip across the solar system and landed on Mars or other places? And the answer is yes, it can. In fact, if you remember the Chicxulub impact, the infamous asteroid impact that occurred 65 billion years ago that devastated life on this planet, including putting those poor dinosaurs in a very bad way, that threw out tons of Earth biomass, not just outside of Earth, but outside, way outside of Earth's orbit and into other orbits, including Mars and even the outer planets. It's gone everywhere. So organic life from this planet has, not just once, but many, many times over the history of biology on this planet, has gone for road trips across the solar system. And the first organic life transport and on this solar system was certainly not by us. It was certainly by nature. And nature delivered Earth rocks to Mars. Now, did those Earth bugs stored in those rocks survive on Mars? Maybe not. Don't know. It probably had a rough landing. Maybe it got too hot during landing to survive. Or maybe it did. And maybe it just when it got to Mars, it did land in a place that was particularly interesting and died off. But I have no doubt that life has the means and the mechanism to transport around our solar system. And so my question is, if there was no life on Mars, why wouldn't Earth life have found a nice warm spot to live on Mars 3.5 billion years ago when there was plenty of it here on this planet?
Do you think we could get the evidence from Curiosity about whether Mars infected Earth with life or vice versa? Could we determine that?
Oh, yes. I think we could.
Wow.
Now, I would, it's, by the way, all of what I just said is still in the area of speculation.
Yes, of course.
And this is scientifically valid sci-fi.
Right.
And so but I can tell you, the more we learn about life and its ubiquity on this planet and its ability to survive, not necessarily individual species like ours come and go, but the overall fabric of life has this incredible tenacity.
Yes.
And if it can just do its sheer numbers, it will try and succeed. And so, that's why many of us, would be shocked if we didn't find at least some simple organic, complex organic structures or even early primitive life on places like the oceans of Europa.
Right.
These are, I know, so Mars is, we love Mars, and I love going to Mars, and Mars is right there next to us and easy to get to. But I tell you, places like Europa, with its oceans vastly larger than our own oceans, surrounded by many hundred kilometers thick of shell of ice, and kept warm due to the tidal forces and squeezing that Jupiter has been doing to its own personal planets, mini planets, the moons of Jupiter. Over the years, I can easily imagine that the energy is there, the will is there, the temperature gradients are there, the chemistry is there to allow for life to exist in those places too. And maybe this is a great place for fishing someday.
I'm going on a fishing expedition to the oceans of Europa.
Exactly right.
Let's get to Mars. Maybe we can go to Jupiter next.
Yeah.
We're going to take a break. I want to talk about the future of Mars exploration, and this is the guy to talk with. Rob Manning is the author of Mars Rover Curiosity, the firsthand story of the design, the amazing landing, and the science that's being done by the Mars Science Lab. It is highly recommended from Smithsonian Books. But what's next? Rob is still at NASA JPL, still working, and I want to know what he's working towards. We're going to find that out in just a moment. I don't know if you saw the Kickstarter a couple of years ago for Smart Things. What a great idea. Smart Things, the folks at Smart Things said there's got to be an easier way to do home automation. And so they actually raised quite a bit of money. They were asking, I think, for $250,000. They got more than $1 million from people to create the Smart Things Smart Hub. And here it is. And let me tell you, this is great. Instead of just talking to other Smart Things devices, and by the way, there are a bunch of Smart Things devices, the Smart Things Hub connects those incredible devices of smart sensors and outlets with hundreds of other popular connected devices, including offerings from Logitech, Belkin, Dropcam, Nest, Sonos, the Philips Hue. It works with If This Then That. They have a Smart Things app. So it really is the centerpiece for a home that does whatever you want with a huge variety of smart things. I guess it's got a good name. For instance, if you look right now, you can go to the Smart Things website, smartthings.com/twit, and look at their home security kits or their solution kits. These are great because they give you a starting point that you can, begin right away. When you get these kits, you're going to set it up, and it took me about 5 minutes. It's all working. Whether you want the solution kit that will control and automate your lights and small appliances wherever you are, or get alerts to prevent a small leak from causing a major flood, or stay connected to your family, getting notifications literally when people come and go. There's even a maker kit for Arduino folks. The SmartThings app is free. It's available for iOS, Android, and yes, Windows Phone. Yahoo! And if you're a developer, SmartThings has an API, so you can create new ways to use SmartThings and publish them for everyone to use. SmartThings just announced that in 2015, you'll also be able to control and automate a variety of Samsung appliances, including refrigerators, washer dryers, air conditioners, even a Samsung robotic vacuum. I love this. So easy to use, and right now with 10% off, so affordable, 10% off any home security or solution kit. Go to smartthings.com/twit. Use the offer code TWIT10 at checkout. For fans of TWIT, the solution kits start at just $170. The home security kits start at $350, and each kit includes that SmartThings hub. That's the smart part, with everything you need to turn your home into a smart home in just 15 minutes. You also get free shipping within the U.S. That's smartthings.com/twit. Don't forget to use the offer code TWIT10 at checkout. Our guest, Rob Manning, is the author of Mars Rover Curiosity, a new book that's covering the inside story, because he was one of the guys in charge of getting the Curiosity Mars Science Laboratory on the surface of Mars, the amazing stuff it's discovered. It feels like, though, we're moving toward, are we moving towards a manned landing of Mars, Rob? Is that the goal?
I don't want to say that's the goal, because there's so much we want to learn from Mars, even before people go there. But on the other hand, it is going to happen. If as soon as, I mean, just like we talked about the web of life, human beings are, we are very much like the rest of the web of life, and that if there's a will, we have, and when there's a way, we can make it happen. And I do think that we have been making major inroads into figuring out what it would take to get human beings on Mars. Now, for a while there, I was and I talk a little bit about this in my book, I was a little shocked at how little we understood about just the very act of getting people from outer space to the surface of Mars. Because I told earlier about just how difficult it is to get our rovers down, let alone a vehicle with that 3 or 4 people could actually land with all their food and water and bedding and spacesuits and air to bring with them. All that stuff has to be brought with them. So I was thinking, oh my gosh, this is really hard. But I believe that since then, especially over the last decade, NASA and JPL and other people have been thinking about this problem, not just of landing people, but all the other issues. For example, what's the radiation environment like on Mars? Can a human being survive the radiation? Turns out Curiosity rover brought with it a radiation detector that allowed us to to measure the radiation a human being would have experienced on the way to Mars, as well as the radiation and the conditions for being on the surface of Mars. I mean, for example, how dangerous would it be? Mars, as you know, doesn't have a magnetic field. It doesn't have, we have this wonderful magnetic bottle that deflects high-energy particles from the sun away from our planet. We have this, ozone layer way above our planet, made up of O3, 3 oxygen atoms glued together, that are really good at absorbing ultraviolet light and preventing that ultraviolet light from our sun from raining down and giving us not just sunburns, but cancer. And so Mars doesn't have that either. So there's a lot of things you have to do to protect yourself on Mars. Good news is that I think that we're now getting our handle on Mars is dangerous, but not too dangerous. We can figure out ways of shielding ourselves from both the sun and from the ultraviolet light. As long as we take certain steps, we can get there. We're also figuring out how to land people there, what kind of things it would take. And
you couldn't use the bouncy, but
no,
could you use the tractor? You could maybe use the...
Oh, I could use, yes, certainly the sky crane is certainly a possibility of lowering people. But the hard part is even getting to that point where you're slow enough to use the sky crane, right?
Right.
I mean, if you're going 1,000 miles an hour, and you're 20 feet above the ground, it's not going to looking good. So you got to so slowing down to the point where you can use things like sky crane or other architectures was sort of been the hard part here. And so we've now working on new tricks. In fact,
exciting.
We're taking lessons, and I don't know if you know, SpaceX recently did a they're spending money to try to figure out how to return the first stage back to the landing spot so they could reuse this equipment, ultimately saving money on their launches. Now, that means to do that, they have to bring in some extra fuel, and then they have to do something that we would do at Mars too, which is very high up when the air is very thin, but you're going very, very fast, is to fire engines backwards into the flow and produce this almost rocket-like comet that flies through the atmosphere, and then before slowing down to the point. Now, great news is that technology called supersonic retropropulsion, SRP for short, is being tested, and in fact, it's been recently tested in their last flight of the Falcon 9. So what's really cool is that they're making progress in the very technologies and techniques that we would need to bring people up.
And of course, just a few days from now, Orion will be tested.
Yes.
Which is the new launch vehicle that could, in fact, get manned.
Yeah. I mean, all the little pieces are gradually coming together.
And yet, I have to point out that we have done so well with unmanned exploration. And a lot of times people say, well, why do we even need to send people to Mars?
Well, if going to Mars with people and signing scientists to Mars was as inexpensive as going to robotic missions are, then we would do that without a doubt. Because I can tell you, like my friend Steve Squires, the principal investigator for Spirit and Opportunities, Mars Exploration Rover Project, he would be doing science about 1,000 times faster and more efficiently than any one of our rovers. And same with our vehicle. Even though we do have a high-tech, shrunken down laboratories that we put stuffed in this vehicle, they're still slow. It's still slow as molasses. I mean, the wheels just rotate just because it's so energy poor. They rotate like this. I mean, we could have a race with a slug and lose. So humans would definitely do better. The problem right now is the cost for a single mission to bring a human to send a team to Mars and back again is extraordinarily high. In fact, it's still decades away. In the meantime, these robotic missions are doing the reconnaissance that you really need. And I tell you, not just the reconnaissance in terms of understanding Mars, but the techniques and technologies and understanding and the visualization of what it takes to do that are all being put together with robotically well in advance of the first footprints on Mars.
That makes sense. Have you and the folks at JPL read The Martian, Andy Weir's book, The Martian?
Oh, absolutely. I'm a big Andy fan. Hey, Andy, if you're listening.
He's been on this show. We love him. Yeah. We love the book.
Yeah, I do too. In fact, I got a chance to hang out with him a few weeks back.
Neat.
And we exchanged a lot of notes. I've been helping a little bit with the movie.
Oh, good.
That's right. Because my little lander Pathfinder, my team's lander Pathfinder, his figures in the movie and in the book. I won't say how.
No, because that would be a spoiler. But Pathfinder is a big character in the book.
Oh yeah, Pathfinder's a character, and so I sent him a bunch of working through JPL. And NASA, we got approval to send a bunch of pictures and images of how the vehicle works, so they can build models that look something like what we built, and that's reasonable. So Andy's a brilliant guy, and I don't know how. I mean, he could fit in our crowd very easily.
Well, the thing that struck me reading the book, and it struck me reading your book too, is that really this is a process of solving a problem, next problem, solving the problem, next problem. There is this really, and I think that's probably very pleasurable. Seems like the human mind works well that way, where, okay, we've got a problem, let's solve it, and that's real satisfying. Now we got the next one. And the book is very much like that. And in fact, when I read this, that's really what you had to do with Curiosity.
Yes. I mean, one of the things that we learn along the way for these missions is because the number of times that we run into what appear to be unsolvable problems or problems that look incredibly daunting, they may be a little depressing at the time.
Yeah.
And you may have to take a lot of deep breaths and
swear.
Swear. But the trick is, don't panic. Stop, think it through. What are the options? Many of the times, the things that look like it's never going to work, they turn out to be features rather than the end of the world. So the trick is to find, to me, where the stress is finding all of these idiosyncrasies about the system making sure that the system, that the parachute, when it inflates, it doesn't rip apart. Make sure that when you're lowering the rover down and the rover is talking to the descent stage over its computer network through up with wires running up a rope, literally. And you want to make sure those wires don't break. You have to do all these little tricks and tests to make sure that everything works just like you think it's going to do. So the real hard part is making sure it's not, I mean, there's many times when you fire something and the test fails, or the design that we thought was going to work doesn't work. But that's okay. We haven't launched it yet. Let's fix it. And that is something that we do over and over again. So the trick is being aware that mistakes happen, or we just don't know enough about how the system works for us to be right until we put it all together and try it out.
I'm reading from the book Mars Rover Curiosity. When we looked, and this is Rob writing, when we looked at the clock drift on both Spirit and Opportunity, to our dismay, we discovered they were both more like the software test bed and the EDL test bed. In fact, the clock drift difference was what had motivated Jim to ask for the test run in the first place. There was a growing chance that neither of the two spacecraft would survive. And I pleaded with Glenn Reeves, the chief engineer for the rover's software, to see if his team could figure out changes to the software that would work around the hardware bug. He shook his head. Rob, it's too late to fix the software. Then we're sunk. My head was spinning. Don't panic, he told me. We'll send the signal to enable the pyros manually. Tomorrow night, a few hours before landing, we could send low-level commands to the rover that will do what the software was supposed to do. Whew. It worked. But then you have a whole chapter following called Gremlins. And I think a lot of this we didn't know at the time, that there were things all along, even as you're about to land, or whatever it is you call it, that Curiosity did.
It lands.
You're about to hit Mars, and all sorts of things are starting to fail. I mean, it's really, this is a suspenseful book.
The thing is, the number of stories that I left out because I just didn't have time to finish them in the book.
There's more?
Doubled, at least doubles. I have tons.
Wow.
That's when I can give talks. I can just go on all day long. I mean, these stories, I mean, that's the thing is, these are very complicated systems and built by human beings, trying to test systems that really cannot really be tested because Earth is not like Mars. We can do all we can to make our vehicles, put it in an environment that makes it look like Mars, but it isn't Mars. It doesn't have the gravity. We don't have the temperatures always right. The atmosphere is made of carbon dioxide, not nitrogen. It's certainly not cold. All these things, are different, and those differences make our system incredibly difficult. And really, I tell people, they feel so well. When did you test Andrew Descent landing? And I said, we didn't. We tested all the little pieces.
But the sky crane had never been tested because you can't.
Well, that's right. Neither had the parachute, neither had the descent stage, neither had the heat shield. Now, when we test the heat shield, let me tell you, we make a coupon about this big around, and we take it to something called the ArcJet facility, which is up at NASA Ames Research Center. They have this wonderful facility to blow this very fine, very thin, but very fast gas on this heat shield, and we watch and see whether, gee, did it melt? Oh, it didn't? It's working. So now we build one that's 4.5 meters in diameter, made of these big chunks of tiles. Okay, we're done.
Wow. I think of all the things humankind has achieved, these are the most amazing achievements. And we're walking right in the middle of them. And I don't want people to take these for granted. We're going to take a break, come back with more. Our guest, Rob Manning, is the author of Mars Rover Curiosity, an inside account from Curiosity's chief engineer. We continue to get science back from the Mars Science Lab. It's an amazing, amazing feat. And we're not done yet. I love this sponsor, FreshBooks. They saved my keister. Back when I was remember I was going to Canada 1 week a month doing a call for help up there with Amber and Andy, and The problem was that I had to bill Rogers for each trip. I had expenses that they paid for, and of course they paid my day rate. And I would invoice them. I hated invoicing so much. I would like invoice them every 6 months. And every time they go, you can't do this. Invoice it at the end of the month. We don't want to have to save up. Well, that's when Amber told me about FreshBooks. And man, did it save my life. FreshBooks made invoicing easy. Now they do even more than they did back when I started using them in 2004. It's a great time to get a fresh start for the new year for 2015 with FreshBooks, the easiest way to invoice clients, organize expenses, and track your time. Their mobile apps are so great. You could do everything you need to do anywhere from Android or iOS. Create invoices online in minutes. Snap photos of receipts right from your phone. Man, it's so cool. Plus real-time business reports in just 2 clicks. And by the way, this is what's awesome. See how good those look? But you're going to get paid faster because every FreshBooks email invoice has a button that says pay it now. And your customers, your clients can use credit cards. There's a whole system of payment solutions that makes it very easy for them to pay you. You know what I discovered? Clients want to pay you. It's just as much of a pain for them to process your invoice as it was for you to make it. So this makes everything friction-free. Invoices can be generated automatically. Payments can be made automatically. You could track time and expenses with your smartphone, and then you're going to get these great reports. Your accountant will love you, and if your accountant is you, you'll love you. FreshBooks grows with your business. Adding clients and projects and staff is as easy as can be, and they have the #1 support staff in the world with FreshBooks Support Rockstars. Free support forever, and you get to speak to a real-life human every single time. I know people who use FreshBooks. I use it for a long time. And I have to say, it is just a great solution. Anthony Taylor, he's the CEO at SME Strategy, kind of, a small business. He says, I'm loving FreshBooks right now. I've been tracking all my time and costing our projects to track my productivity. Information is power, my friends, and FreshBooks makes you powerful. On average, you'll get paid 5 days faster. And on average, FreshBooks customers double their revenue in the first 2 years. Wow. FreshBooks, try it free for 30 days, no obligation. FreshBooks.com/triangulation. And if they say, how did you hear about us? Just put the word triangulation in that field so that they know. That's how we pay for this show, so it'd be very nice if you did that. Start your 30-day free trial today. Go to FreshBooks.com/triangulation. And don't forget to enter triangulation in the How Did You Hear About Us section. FreshBooks, we love it. Our guest is Rob Manning, author of Mars Rover Curiosity, an inside account from Curiosity's chief engineer. This is Smithsonian Books. Get it, read it. Like I said, if you liked Andy Weir's The Martian, this is the real deal, minus the profanity. And in fact, I'm looking at the route that Curiosity is about to take up onto the mountain, and this reminds me a little bit of the route that Andy Weir's astronaut had to take to save himself. I mean, it's just fascinating. This is really happening.
This is really happening.
And so exciting. So neat.
I hadn't actually seen this latest update.
Oh, all right. Well, let me show you. This is it. This is on the JPL site.
Yeah, no, I know exactly.
So you changed the route. Why did you change the route?
Well, there's a couple of reasons. I think that, the biggest reason is, and this goes back to kind of the limitations, the failures of our imagination. We made, you may have heard that our rover wheels were not happy living on Mars. I mean, the rest of the rovers loves Mars, hates Earth. The wheels, on the other hand, were another story. We made aluminum wheels. We used the very same articulated wheel system called a rocker bogie system that we use on Little Sojourner, on bigger Spirit and Opportunity, and now Curiosity with these big movable, it's in fact, it's architecturally just like a 6-point mobile that you hang with different weights. It allows the wheels to spin, to tilt with the surface. However, we made the wheels as light as we could get away with, and we tested those wheels here on Earth using our simulated Mars surface. What does a simulated Mars surface look like? Well, it looks like the desert.
It's a lot of rocks. In fact, when you look at the pictures of Mars, you feel like you're almost at home. We could be in I don't know, New Mexico, or it looks like the Nevada desert.
It is very terrestrial-like in that respect.
This is it, Jason, if you want to show it. This is a picture from Curiosity. I mean,
yeah,
I could be at home.
There are some interesting features that are also present on this planet, but not as common on Earth as they are on Mars. And one of the things is when you take a rock, a boulder, even if it's made of hard lava, and you leave it on Mars' surface, and provided it doesn't get covered with sand dunes or something like that, it just sits there in the Mars winds. Now, Mars has atmosphere only 1% of Earth's density. We talked about how thin it is, but it can actually get some pretty decent winds, high-speed winds, not as windy as Andy Weir's windstorm at the beginning. I won't give it away,
he says that's the only mistake he made, but he knew he was doing it. He had to do it for the purposes of the story.
Exactly, and it made sense.
Yeah,
great device. And but over hundreds of millions of years of these very fine smoke-sized particles, or little tiny grains of sand, hopping and skipping over the surface of Mars, grinding away at these rocks. Over hundreds of millions of years, those rocks don't look the same. They start getting sharp, smooth surfaces. They are sculpted by the wind and the trained dust to these sharp little points. Now, we tested those points, but we put these rocks not in, we put them on the ground. And so when the rover drives over these sharp points, what does the rock do? It goes, bends over, and it conforms with the shape of the wheel. What we weren't expecting, and we didn't use our imagination because we should have known better. In fact, many of the scientists knew better. They thought we knew. Turns out that when you embed these rocks in clays, they get glued in place. And then they get sharpened up. And when you drive over, it's like a bed of nails. Even the littlest rocks.
Well, you can see this in this picture. You wouldn't want to drive over these if they didn't move. That's sharp.
Yeah, they are sharp. In fact, they'd be really even hard on the soles of an astronaut's feet. And so what we realized is that those sharp little points were poking, because they didn't give, they were poking into the aluminum wheels and poking holes, and now the wheels have rather large tears in them.
Oh dear. They're not inflated tires.
No, they are. They're big. Starts off, imagine this big block of aluminum, and you take it with a milling machine, you grind it away, leaving the shell of the wheel, basically the tire, and then the inside is connected through a series of spokes to give a little plasticity and bounce to the as you drive over rocks to the axle, which is where the electric motors attach. Right. So these wheels, which are about this big in diameter, are very lightweight. I forget how
thin aluminum is it. So it seems hard to believe that it could get punctured.
Well, because it is thin, and in order to save the weight, because we did have weight challenges, because when we first built the rover, the most we could carry, we thought was about 950 kilograms. When we designed the wheels, we were afraid the whole vehicle was going to end up weighing at least that. Over time, things actually got lighter. We actually realized we were saving some masses here and there. So the whole vehicle ended up launching about 900 kilograms. However, despite the lighter rover, we put a lot of effort into making the wheels as lightweight as possible, and we tested them, and they seemed to survive rocks that weren't bolted in place. And so we said, well, even though they're really thin in places, that should be fine. Well, it wasn't fine, and we stopped thinking. And I can tell you, every time we've stopped thinking about a problem or fail to ask yourselves, well, just how bad could it get? Then we lose it. And so we failed one of our own lessons that we've learned over and over again. And I personally should have known better. I saw pictures of the test results, and it looked, well, it was okay. It looked pretty good. Right. I didn't really poke and say, well, how bad could it really get? How could those rocks be locked in place?
So the new route avoids rocks, or I mean?
Yes, it does. It tries to avoid. Okay. It tries to live in the. I mean, and you can see from space the kinds of conditions that allow to take place.
This is a picture from the mast cam of Curiosity, and that's about a 6-foot wide swath. So you can see, really, this is treacherous terrain that's crawling over.
Yeah, those rocks are really sharp. And look how you can see the clays that are laid down.
Boy, it really does look like water was there, doesn't it?
It really does. It was, and you can see it's really wet. It was wet. Now those clays are older than any clays that you'd find on this planet. I can tell you that. I mean, you have to really go down deep and look at buried layers, like the bottom of Grand Canyon and other places, to go back even remotely close to that period of time. In fact, you won't find it unless you're very lucky. But cool. here, so we're looking at a museum.
It's amazing.
Yeah.
And what a great picture. I mean, the quality of the image is stunning.
I know it's great. Yeah. Well, this picture was taken by Mike Malin's mass cam. I believe it's a mass cam.
Yeah, it's the mass cam.
Yeah. And it has to be from, you can see the arm. And so, it's just, they're HD quality images. I mean, they're really something that, and what's more is the color is so much more precise. You know, there was a long time we were taking pictures with black and white cameras. We put a color filter in front of the camera lens with a little motor that would rotate the lens in front, the color filter. And we could never actually convince ourselves that the colors we were seeing were the colors that we would see if we were human beings. So, because we would constantly kind of tweak it into a little bit pink, too orange, too gray. So these cameras, on the hand, give us a much closer sense of what it would look like if we were physically there on Mars.
I just want to show you, not you, the people at home. You've seen this. This is the self-portrait. If you put together all of the images, this is what Curiosity looks like. Imagine a Martian coming upon this. Humankind visiting the red planet for the first time, a science lab, able to really analyze what it's seeing, take amazing pictures. There's the mast cam. Just so exciting.
You can see the drill hole down in space.
That's an actual hole, yeah.
And a lot of people ask me, okay, who the heck took this picture?
Well, Buzz Aldrin, of course.
Buzz. He does wish he was there, too.
Oh, I could tell. He wrote on the front of your book, he says, this is a matchless behind-the-scenes account of intrepid engineers and scientists who band together to explore faraway Mars. It is superb, fact and fun-filled account of humans on the cutting edge of opening up a frontier, our future home away from home. I bet Buzz would love to step foot on Mars.
And I think he would actually love being part of our operations team because when you operate a rover on another planet, at one hand, we have to train our rovers to do everything. These are not joystick. These vehicles.
No, because there's how many minutes is there between in communication?
Well, it varies anywhere from less than 5 minutes all the way up to 22 minutes.
So you can't
one way.
Control it. Yeah.
And so, but not just that, we don't even have the radio power to keep the communications going. So what we do is when the rover wakes up in the morning, because Mars has a 24-hour and 39-minute day. It's very convenient if you're working on Mars time. You can sleep 39 minutes every day. Isn't that cool? And so you can. So when you come into work, overnight while the rover's asleep, or even earlier, we put this little script together of things we want. A list, a things to do list that allows the rover to. When the rover wakes up, we send it to the rover. The rover barely says thank you. It says beep. Okay, got it. Thank you. And then we don't hear from the rover all day, and it follows the script and includes driving over there, collecting samples, looking at the atmosphere, controlling his laboratory. The rover has all these different hobbies it's got to be good at, and it just gives a list of all the kind of hobbies it can do. Some of it can do in parallel, and so it does that throughout the day. At the end of the day, one of our orbiters flies overhead, and the rover automatically knows it's coming, and so it throws all this pictures, data, up to the orbiter. The orbiter says, thank you, got it, and flows it back to Earth, back to the Deep Space Network, where we can get the data. So it's really very robotic. On the other hand, when you're actually looking at the data and you're planning what's going to happen tomorrow, you're wearing stereo glasses, you're looking at the world through 3D, you're looking at the whole scene, you can operate a virtual rover and a robotic left arm rover arm.
You're there, man.
You are there. These rovers are extensions of us as human beings. Yeah. It's not simply a matter of these rovers being a bunch of, aliens, robots going out there doing a bunch and letting us know how that's going. It's much more than that. They really are extensions of us.
It must be hard not to anthropomorphize. I mean, when I look at this selfie of Curiosity, I feel like even me, and of course you know this intimately, you knew it on Earth, even I look at this as a sentient being almost. It looks like it's looking at us.
It does have, we go both ways. At one moment, it is a thing on its own, and that we treat like it's a living thing. And the next minute, we're inside it, part of it.
You are
reaching out from the eyes of the vehicle itself. That arm is our arm. The wheels are our feet.
Wow.
And so we can go both ways on it. But it is not. Especially since we know so much about its innards, we can really sense what that vehicle feels like to be on Mars.
Oh, man. How exciting is this? I've kept you way too long, Rob. I apologize if you need to go do. One more question. What's next? What are we working on next? What's the immediate goal right now? I know you're not done.
No, there is another lander, a legged lander, not a rover, that's going to be landing on Mars in 2016. It's called the InSight lander. It's a sister to the Phoenix lander that landed at the North Pole of Mars in 2007. If you remember, it was able to, when it landed to the North Pole, it scraped the top surface of the North Pole and found ice.
CO2 ice.
Water ice.
H2O ice?
Water ice. Water ice was everywhere, just inches below the surface of the north half of the planet. Mars is it's frozen solid, but it's full of water. There's still a lot of water remaining on that planet. And so Phoenix was a huge success in terms of its understanding of not just the poles of Mars, but also where the chemistry of the remaining water that's still there. So that same lander is being altered to be a seismometer. It's basically a station that's landing on Mars. It's going to analyze. It's going to sense the thermal heat that comes out of Mars. See if they can find Mars quakes. See how active is Mars as a planet, and that's coming up pretty soon. So. But the other thing was, meanwhile, we're building up another rover, a rover that's just like Curiosity, except unlike Curiosity being a roving laboratory, this is going to go and collect core samples. It's going to do science, but it's also going to collect lots of core samples and then pull them together into a pile and put them down after years of looking at rocks and collecting core samples. It'll put this pile of rocks into a place where a future mission can land next to it, grab those core samples, and launch them in a rocket to put into orbit around the sun, around Mars, and put them in a spacecraft about this big around. So that spacecraft's going to have those core samples in it, and it'll be in orbit for months or years before yet another orbiter comes along, gobbles it up, flies it across back to Earth to be collected and analyzed by scientists on this planet.
Unbelievable. As somebody, and we're, I guess, close to the same age, who grew up watching the, Gemini and Apollo, and was so inspired. And sometimes, I don't know about you, well, you probably knew better, but after 1969, I kind of felt like, we're done. I wish we would continue this. This is the good news. We are.
We did. We did continue.
It's still going on, and I'm so happy to hear it. Yeah, and whether we land somebody on Mars in my lifetime, and I don't know if that'll happen, but I think we will, and I think the progress continues, and we are learning so much. And,
and there's a lot more to learn. I mean, it's not just the stuff that we're doing. Every time we send a new mission to Mars, it opens a whole other chapter of understanding, and we are further humbled by just how rich the story of nature is, not just on this planet, but all the planets. And that's why we would love to not just continue Mars, we would love to continue other places. We want to go to Europa. We want to go to Titan. We want to go to the outer planets. We want to spend explore all the planets, because we are all one part of a giant system. And perhaps the web of life that has been so successful on this planet was able to reach out and evolve outside. Or perhaps, maybe, life started elsewhere, and we are descendants of Martians. I mean, we don't really know, but these are the kinds of ideas and thoughts that we've got, and we're trying to find out.
Rob Manning, thank you so much.
Welcome. Thank you, Liam.
Really great to talk to you. Mars Rover Curiosity, an inside account from Curiosity's chief engineer. And we'll just say goodbye to the selfie of Curiosity sitting there on Mars, ready to make its trip up the mountain and continue its work. And thank you, Rob, for making that possible. And all the amazing engineers and scientists and people at JPL and NASA. Thank you, Rob.
Thank you.
We do Triangulation every Monday, 11 a.m. Pacific, 2 p.m. Eastern Time, 1900 UTC. Please watch live if you can. If you can't, don't worry. On-demand audio and video always available after the fact. twit.tv/TRI, youtube.com/triangulation, or better yet, because as you can see, every episode is a gem. Subscribe, and you'll get episodes each and every week. And there are plenty of ways to do that with iTunes or Xbox Music, or use your podcast app on your smartphone or your mobile device. But don't miss an episode, because it's always so exciting when we get together for Triangulation. We'll see you next time. Bye-bye.